Hi, you're very welcome to the recording of the fourth lecture in topic 8, which is higher order functions, and this is on function composition. Okay, so we'll just get going on this. So we are looking at the idea of what happens when we have a lot of, it looks like jumbled up calling of functions and calling of functions on functions and so on. So we're looking at how we can compose these, and basically we can see that if we have this idea here, and what that means is that we apply g to x, and whatever the result of that is, we apply that to, we apply f to that amount. And if we can do that, we kind of take this pattern here and we say we can rewrite it like that on x. Okay? So you can see here that what we're looking at here is we have a, first of all, we do the function g first because it's over here. All right, so g goes from apples to lemons. So g takes in apples and basically gives out lemons. F expects lemons and will give out oranges. Okay, so and you can see it written here as well, more generically. And you can see that G, you can see the apples as A and B as lemons, and F goes from B to C. So sometimes the tricky bit is remembering that because G happens first, if you like, the outside and the final type goes from A to B, and B is the common type there, the common type. So the composed function is from A to C. So you send in A's and you get C's. Okay, so what we're trying to do is take a group of functions, which is like, a stream or a chain of functions like that, and we want to rename it like that. So you can think of that, those functions up there, that's g first and then f, so it's g composed with f, and we write that as f dot g, okay, because g happens first. So it's just a little bit of getting your head around that, okay, about the order. Okay, so using lambda, you can see what's happening here. We have, remember, this is infix, infix because we're going to say f dot g. So remember, f, remember, is the second one to be called. So the first one to be called starts with an A and gives out a B, and the second one to be called takes in that B and gives me back out a C. So what it does is it takes two functions and returns a function that takes in A and gives back a C. So the A comes from here and the C comes from here. Those types could be the same. And what you're saying there is that's the same. FG is the same as saying F applied to what's returned when you apply G to X. So you can see here we're renaming the functions and we're using the lambda here, so we could use that anywhere. So we're actually dropping the x on f and g. And we're saying, just give me some g there, any g, any variable, and we'll do it with that. Okay, so the input parameter must be the same type as the return type of g. So it's a chain, so you need to, and remember the apples and the lemons and the oranges. Okay. And we often say it's convenient to create functions on the fly, which means we have a necessity to do maybe two things, and rather than write the two things or the one thing that contains the two things, what we will do is take two predefined functions and put them together if that is appropriate. So for instance, we could say here we're using a lambda to do this. We're saying map this function. Now if we look at the way this is, remember what map does? It takes a function and it takes a list. So this is the function. All right, so this function is expecting a list. So you could also, so it's expecting, so the x is, remember it maps on each element of the list. So that's your x, that's why it's not called xs. And what you're saying is, for each element of the list, we're going to negate the absolute value of x. So you can see there, if we think back at the previous definition, this is your f and your g. So g happens first and then f. And it's applied to that. Sorry, that's the result. So you can see what's happening here. You're getting the absolute value of -5. Sorry, that's 5, and you're negating that. The absolute value is 3, you're negating that, and so on. Okay, so you can see that, or hopefully you can see that this is the same as that. Okay, and just remember that it's coming from this, right? So that is, if you can write it like that, you can write it like that. Okay. Right, so why do we do it? So if you look at this is another one, right? What we're going to do is we're going to say map. In this case, we're going to say map all of this, all right? But we don't know yet. We're going to apply that. So this is the function that we're going to apply. So we want to look at this function and see, could we simplify it using the functional composition. So remember the XS, this is actually the XS here. Okay. So that returns this. Okay, so what do we do here, right? So we're going to map negative to sum. So what's the tail of 1 to 4? Well, the tail of 1 to 4 is the list 2, 3, 4, 5. The sum of that is 14, and the negative of that is -14. Okay, so this is just a way of showing you how you calling one function and applying one function after another in a chain. So that's the same as saying take the tail take the tail of, your list, get the sum of the tail, take that number and negate that number. And you're to do this to each one of the elements of this. So remember, in this case of the list, each element of the list is itself a list. So it wouldn't be applicable if that. Obviously, all the types have to be consistent. So if we apply that to that, we expect to get the same result, and in fact we do. Okay, so eta conversion, we met this in the original lambda calculus, but basically what we're trying to do, and the terminology we'll use, I mentioned in class already that there's different terminologies for this, but what I'm going to say is drop as many variables as you can. Okay, so that can be rewritten as this. So you can see here, oops, I just changed that. So the first thing to happen is k is applied to x. So we have k here, and then j here, and then and so on. So you can see the i's here. Then you have your h, you have your g, and you have your f. So here's our x, and the order, and there's not, this is basically just a stream. You're applying the k, then the j, then the I, then the H, then the G, then the F. And this is all done to X. All right? So we can rewrite it like that. So anytime there's, if you like, the straightforward chain of functions like that, you can rename it to the using the function composition. And there's an added one here then. If the x appears here and here, then you can drop both instances of it like that. And what you're saying there is that I've another name for this big long, in fact, I've another name for this, this big long bracket, and I'm just going to call it my func. Okay, so I can just call my func on anything of type A, and I'll get back type B. All right, now we're assuming that all the types matched up as we needed to, with our lemons being in the middle from the previous one. So, okay, so this is the next one. Now we looked at this in class as well, but just to run through it again. We're assuming that cube has what you would call, if you like, what you would expect as the definition of it. So cube is take a value and cube it. And then by 7, just checks, is a number 7, okay? That's by 7 there. Okay. So we're going to try and rewrite it and then get rid of the x's if we can. Okay. So we can't, you see, get rid of the x's or the xs in this case because it's a list when it's in the middle of a bracket there, because we don't know how entrenched it is in the others. So the first thing we're going to have to do is to try and rewrite that using function composition. So the first thing we're going to do is filter by that. So we're going to still have a list. Then we're going to map cube to that list. So that's going to cube each element of the list in that. And then we're going to get the sum of all of those. So filter by 7x XS here. That filters all the numbers divisible by 7. Map cube here. Cubes to filter numbers. So you can see the chain is there. So filter gives me back a list. Mapping cube across that, these are numbers, it's a list of numbers. So filter will still give me a list of numbers, no matter what the filter is for. Cube is a function that takes a number and gives me back a number. So mapping, so my types are okay. So I'm going to map cube across that, so it's still a list of numbers. So it's okay for me to do sum on that. Okay, and then we have our sum on whatever value that is. Okay, so you can see what's happening here now, right? The filter by is acting as input to the, the cube part of the map on that. So we'll have a look. So remember, this is the other one. If we can say F, remember the big long one included this. F applied to G applied to H, X is the same as F dot G dot HX. And that's what the one previously looked very like. So we can say, get the sum, apply the sum to what is returned when you apply map. And remember, map takes two parameters. It takes the function and it also takes a list. But in the previous one, I would have had here, I could have written this down here as XS, and here I could have XS out here as well. So I can drop it in both cases. Okay, and that's, so just to go back over it, filter by 7 produces a list. Map cube transforms that list using the function cube to do that, to change each element of that list, and sum takes that list and reduces it to a single value. So as function composition applies functions from right to left, that's the same as that. And that's equivalent to that, because what we're saying is that sum happens after this all happens, and map, what you're doing is you're mapping, you're filtering the list by 7, and then you're mapping cube across by that. And again, check the types on this if you want to be sure. Okay. So if we run answer, which is this one, filter by 7, that's going to filter by 7, that's just going to now remember what filter by 7 was. It just means it's divisible by 7. Okay, so anything that's divisible evenly by 7, we'll work on that. So we're going to filter by 7, and that's going to give me back just 7, 14 and 21, because 1 is gone, it's not divisible by 7, it'll give me a mod of 1. Map cube on that will take each of the numbers and cube each of the numbers. So we have 7 goes to 343, 14 goes to that, and 21 goes to that. Okay. And the sum of that then just gives you this number here. Okay. So answer started off with a list of integers and gave me back an int. So you can see here, this is the int it produces, and this is the input. Okay. And that's the answer. Okay. So more on that then. When you have that, we call this object level, but I mentioned in class as well, it's all that means is it's really the difference is that excess is mentioned explicitly in both sides of the equals. But remember that the idea here is this: if excess appears here and here but nowhere else, you can drop both sides. And when it's the rightmost term on both sides. And we call this the function definition. But when I'm talking to you, I'll just be saying either with or without the parameters, you know, the arguments. Okay. Right. So that's with single single arguments. Okay. So obviously, as we go through things and things are more complicated, we'll be getting multiple arguments. So we're going to see what we can do with this. So for instance, in this case, we're going to look at replicate. Now remember what, just to remember what replicate does. Replicate five, 2 will give me the list two, 2, 2, 2, 2. Okay, so it replicates that. Okay. So true, right? That max 6 of 9, we're going to apply to 6 and 9, or if we were, what max does is it simply takes two numbers and gives me back the larger of the two. So replicate 5, 9. So if that was the case, it produces 9, 9, 9, 9, and so on. So it's just a way of creating a list with equal elements. And again, like a lot of these things, it's handier than it looks. And the sum of that then. So if that's basically if we're applying this to replicate 5 max 8, 9. Okay. So to do this, our process is, first of all, write out the innermost function and its parameters. So this is, and then compose all the prior functions by omitting their last parameter and putting dot between them. So we'll have a look. So this one here, we had 5 in here, but we're going to change that to n and put that in as a parameter and argument, and then obviously our x and y as well. We have here. So we're going to write the innermost function, all right, and put a dollar beside it. So that's this one done here. And once we've that done, right, we just have a look at what's over here. And we still have replicate n. So you can see here, that's going to give me back this function here is going to give me back a number. Replicate n on that number is going to give me a list of numbers of that type. So that's going to give me sum of that number. And now, how many of those can we get rid of? We can get rid of the x and y because it appears here and they appear here. We can't get rid of n because it appears in the middle. Okay? So here we have our excess here and we have our excess here. That can be written filter odd, map square. So that's what that is going to do, is it's going to take a list, excess, and it's going to square each of the elements. We're assuming square means square the elements, and then we're just going to just keep, if you like, the returned new list will just have the odd elements of that, of the first one. Now, we call the one on the right, where you take the first one and give me out the second one, we call that eta reduction. So that's eta reduction, because what you're doing here is you're taking the s and your excess and you're dropping it. In the other one, you're dropping the excess. You can see that there. All right. So you're taking the dropped one and you're saying, well, I'm if there's something here, there must be something here. So I'm just going to put excess on that. Okay. We're going to try and eliminate the arguments as much as possible, but just to know, you can go forward, you can go backwards. Okay. So that's the idea of functional composition. Now, again, as usual, I absolutely say to you, the exercises are there, they're published. Have a look at the exercises. Don't be tempted just to accept what VS Code does, because it'll look, the answer always looks really obvious until you're actually looking at the other thing. Okay, so thanks a million for that, and we will, the next recording then is on the I/O interaction. Okay.